HighBridge, a division of recorded books, presents Hoofbeats, How Horses Shaped Human History by William T. Taylor. Read by Tristan Morris. Prelude. In the heart of the Mongolian steppe, in the cold interior of eastern Eurasia, sits the grassy Hungai mountain range, home to one of the world's last true horse cultures. Mongolia is changing fast. The country's bustling capital is a hodgepodge of business, education, international trade, and migrants who have left the countryside for urban life. In rural areas, motorcycles are seen in greater numbers each year as herders, scrambling to keep up with the demands of a globalizing and warming world, seek alternative modes of travel. But in the Hungai Mountains, life still moves to the beat of horse hooves. At the southern edge of this high range, there's a nondescript grassy knob overlooking a small bowl-shaped valley called Morin Mort, which translates roughly to Place of the Hoofprints. I have come to Morin Mort with a small multinational team of researchers in search of clues to the early history of people and horses. By early September, when our team arrives, the valley is nearly empty, with most of the local herders having already moved to their fall camps some distance away. The light drifting of early snow that dusts our camp one evening speaks to the logic and precise timing of their migration. On this chilly fall morning, the valley, although now less populated, is far from empty. In fact, it is filled with clues to the earliest history of domestic horses. Around 1000 BCE, horsemen of Mongolia's first horse culture erected a series of monuments known as deer stones, large stelae, sometimes 3 or 4 meters tall, thought to depict ancient warriors. Each is equipped with necklace, earrings, and a tool belt, daggers, bows, shields, and even small horses, alongside elaborate deer images from which their name derives. Some scholars think that these deer images were meant to represent tattoos. Each stone is unique and probably represents a specific person, a brave warrior fallen in battle, perhaps, or a family ancestor. It is not the deer or the stones, however, that have brought us to Morin Mort. It is the horses. Surrounding each monumental stone at Morin Mort is a small ring of individual stone mounds. Inside each mound is the head, neck, and hooves of a horse. During a ceremony, stones were erected and each horse was killed, skinned, and eaten before being carefully buried around the stone, probably to guide or carry the deceased in the afterlife. Today at Morin Mort, only 2 stones remain standing. However, based on our survey and excavation of the site's remaining architecture, we can guess that when the site was constructed, there were at least 5 stones surrounded by more than 100 individual horses. While this seems impressive, the number of such stones at other sites dating to this time is staggering, reaching into the hundreds and even thousands. 3 millennia ago, horses were the beating heart of both economy and culture. Atop a small ridge overlooking the stones and burials, we find hoofprints. At most times of the day, the small flat outcrop of blue-gray sedimentary stone is barely noticeable. A passerby is likely to walk over them without a second thought. But at dawn, and again at dusk, something remarkable happens. With the sun on the horizon, the drab stone panels are illuminated, and the dancing shadows reveal perfect hoofprints carved into the stone. The effect is astonishing. The panels have been transformed into something like a muddy racetrack after a heavy rain. When I first laid my eyes on the carvings, I could have sworn that they were fossil tracks of ancient animals rather than rock carvings, also called petroglyphs. At this hallowed place, the relationship between humans and horses is literally inscribed into the fabric of the landscape. Through the scientific study of places like Morin Mort, my many colleagues and I have tried to understand the origins of horse domestication and the ways that it has shaped the world in which we live. Many scholars, historians, researchers, and storytellers on many continents have taken on the task of exploring these questions. In my own retelling, I have drawn on a wide range of historical documents, linguistic analyses, oral traditions, even modern veterinary work. But our most important clues come from places like Morin Mort, places so ancient and so far from the Western world that they can be understood only through archaeology. It is precisely these pieces of the story that are the hardest to convey and the most commonly omitted from popular narratives and popular science. It is time to give archaeology its due. Time now to use the scientific study of ancient horses themselves to tell the human horse story. Reading the archaeological record is a messy business, fraught with trial and error, mistakes, revisions, and debate. In the 21st century, the toolkits of the archaeologist have expanded from the trowel and brush into the realm of ancient genetics, stable isotopes, and biomolecules. These techniques are changing and diversifying at an astonishing pace. In this book, I bring together the latest knowledge from across the archaeological sciences to tackle old questions with fresh eyes and to rewrite pieces of the story that only a few years ago we simply took for granted. This book is structured in 4 hoofbeats, corresponding to 4 key stages in the relationship between humans and equids. In Beat 1, Horses and People, I explore the origin and evolutionary history of horses and humanity's oldest relationship with the horse as predator and prey. In Beat 2, The Cart, I trace the earliest emergence of domestication. Based on careful reanalysis of archaeological data and important new discoveries, I demonstrate how horse domestication began with the innovation of the chariot, spreading people and horses across much of Inner Asia. In Beat 3, The Rider, I explore innovation in horse control and how the emergence of mounted horseback riding transformed ancient Eurasia and repositioned the steppes as the center of global cultures, economies, and empires. Finally, in Beat 4, The World, I explored the journey of the horse over the globe's great oceans as they accompanied Viking explorers to the high Arctic, sparked drastic social changes across the Americas, and revolutionized life in the colonies of Australasia. In the book's final chapter, I wrestle with the rapid disappearance of horses from a post-industrial world, and I outline how these hoofprints continue to shape our lives and our future. In this journey through the archaeological record, I hope the listener will come away with both an appreciation for and a healthy skepticism of the contributions of archaeological science to our understanding of the world we live in. More importantly, I hope to stimulate listeners to recognize the beats of the human-horse relationship that continue to reverberate in the world around us, from the Rocky Mountains to the Hungai Mountains, and everywhere in between. Beat 1. Horses and People. 1. Evolution. The story of the horse began with a bang, the biggest bang, perhaps, that our world has ever seen. Roughly 66 million years ago, a massive asteroid struck the Earth in what is now the Yucatan Peninsula in the Gulf of Mexico. This cataclysmic event irrevocably changed the course of evolution and life on Earth. In a geological instant, the toxic atmosphere, acidified oceans, and impact winter, a sudden temperature shift brought on by the obstruction of the sun's rays that followed in the wake of the impact, many of the planet's animal and plant species were extinguished. This collision is thought to have caused the Cretaceous-Paleogene KPG extinction event, a mass extinction that brought about the end of most of the dinosaurs. In the desperate ages that followed the asteroid impact, large creatures that roamed the desolated landscape either went extinct or were forced to adapt to a global ecosystem drastically shaken from its lowest ecological foundations. In the chaos, new opportunities also opened. The startling scale of these extinctions left many ecological vacancies formerly filled by extinct animals, ready to be filled by those that had survived. In a process known as adaptive radiation, some groups of animals, including mammals and avian dinosaurs, birds, rapidly diversified to fill the ecological landscape vacated by those that perished. Fossil evidence shows that during this period, called the Paleogene radiation, a tiny shrew-like arboreal creature, the first recognizable primate, flourished in North America and Europe, the progenitor of what would one day become humankind. The Dawn Horse. After the extinction event, in a period known as the Eocene, a very different group of animals appears in the fossil record of the northern continents. The Dawn Horse. Members of the order Perissodactyla, or odd-toed ungulates, These herbivores had 3 toes in the hind limbs and 4 in the front. Although scientists refer to them as equids in recognition of their role as the oldest members of the family Equidae, dawn horses were nothing like the tall, muscular beasts that we know today. The first dawn horses were probably browsers, meaning that they subsisted on leafy forage and brush from forest environments. They were also tiny. The first well-described dawn horse known from the fossil record, classified today as Eohippus, stood only around a foot tall. In the post-impact world, both the dawn horse and proto-primates made their living in the forests and forest margins of a world recovering from catastrophic extinction. Although early perissodactyls were already quite different from early primates, Eocene horses had some surprising similarities with their tree-climbing brethren, particularly in the shape of their teeth. Finding the tooth of a relative of the dawn horse, early paleontologists once incorrectly took this discovery as evidence that monkeys once lived in British Isles. Over the millions of years that followed, the first ancestors of humans and horses would follow increasingly divergent evolutionary paths. Primates, adapted to flourish in forest environments, thrived in parts of Africa. Some of these species developed high intelligence and bipedal locomotion, perhaps adapting to a co-evolutionary relationship with fruiting plants. Within the last 5 million years, some bipedal primates left the closed forest and adapted to the savanna, becoming skilled scavengers, hunters, and gatherers. Sophisticated tool-making skills, intelligence, and cooperative behavior made early humans the top predator nearly everywhere they went. The evolutionary path of the dawn horse would also take it out of the forests, albeit much earlier than our own lineage. More than 50 million years ago, the tiny dawn horse was already excellent at a skill that would define many of its descendants: running. Eohippus was equipped with long, slender limbs capable of long strides and a spine design that kept its head stable while running. The descendants of the dawn horse would come to include some of the world's fastest animals, fueled by the emergence of yet another type of new ecosystem that would redefine equid evolution and human history: the grassland. The evolution of grasslands. If horses and humans are the lead characters in this story, then grasslands are undoubtedly the stage. Today, grasses, stocky, vascular plants belonging to the family Poaceae, include everything from the Kentucky bluegrass of suburban American lawns to bamboo, wheat, and the crops used to make the bread in our kitchen pantries. Members of this family live in arid, well-drained environments, and their high silica content makes them hardy and difficult to chew, digest, or destroy. Originally a tropical plant, grasses also benefited from the mass extinction event, becoming widespread but not predominant in the post-apocalyptic landscape. At first, grasses might have operated as minor parts of forest ecosystems, living in forest openings and understories. Although the causes of this transition are debated, by around 20 million years ago, new ecosystems that were dominated by grass proliferated across the open habitats of the world, occupying vast stretches of land on some continents. These green seas offered a wealth of plant food for the enterprising herbivore, if they could survive it. This was no easy task. For an organism to get enough energy to survive a diet of such harsh, high silica materials requires huge input volumes. With the abrasion from grass, along with other dust and grit common in arid habitats, each bite also causes serious damage to the teeth, which are necessary to grind and chew rough grasses before they can be processed by the digestive system. Grasslands also offered major safety concerns: few accessible sources of water and exposure to extreme hot and cold temperatures. With no vegetative cover, all but the smallest herbivores would have been dangerously exposed to predators. To survive in the emerging prairies of the ancient world, herbivores needed innovative solutions. A grass-powered machine. Horses were once considered a textbook example of linear directional evolution, a glorious sequence of improvements to the primitive Eohippus that culminated in the modern horse. However, we know that this line of thinking is flawed. Evolution is messy and works through incremental adaptations to new circumstances, ambivalent to any long-term goals. The family tree of perissodactyls looked less like a linear progression and more like a braided stream filled with animals large and small that were adapted and adapting to any array of habitats and ecological niches. From the Eocene, the perissodactyls became a diverse group that exploited a wide range of habitats, giving rise to animals such as the jungle-foraging tapir and the armored, wetland-loving rhinoceros. This diversification also produced the first proto-horses, strongly shaped by the special conditions of the open, dry grassland. Over millions of years, some early members of the horse family developed behavioral and anatomic tools that enabled them to survive and thrive in the dry prairie. These adaptations fall into three general categories: energy, speed, and communication. Energy. The most fundamental challenge of adapting to grassland was finding a way to eat it. How can a large organism live on a diet of thin, rigid plants so knife-like that they are referred to in English as blades, and whose cellulose and silica walls make them exceedingly difficult to digest? One answer lies in the horse's specialized teeth, which are the horse's first line of attack against grass's impressive defenses. Horses have pincer-like front incisors, capable of snipping grasses from their stem, after which the plants are moved to their cheek teeth, a long single row of 6 molars and premolars on each side of the mouth. Each of these cheek teeth consists of a flat surface interwoven with sharp ridges of mineralized enamel. When horses chew using their characteristic circular chewing motion, the plant material is both crushed and ground, breaking down the tough protective coatings that make digestion difficult. After a few million years of grassland life, early horses also made a new and particularly critical innovation. Members of the proto-horse group, equinae, became hypsodont, meaning that they developed high-crowned or tall teeth, which effectively served as hidden reserves of extra tooth above and below the gum lines. As grasses wore down the tough tooth surfaces over the course of an animal's life, ancient proto-horses were able to gradually replace lost tooth surface with reserves. A second key to grassland energy among early horses was in their digestive system. Some large herbivores, among them cows, deer, and sheep, responded by innovating what is known as a ruminant stomach. The ruminant stomach uses a 4-chamber structure that first ferments freshly consumed grass materials to break down their rigid components. Fermented material is regurgitated for more chewing before moving into lower chambers where nutrients are absorbed. Horses have only a single-chambered or monogastric stomach, similar to that found in humans and dogs. On its own, the monogastric stomach is relatively inefficient at processing fibrous plant material, which speedily moves through the body undigested. This fact is one reason that fiber supplements are often prescribed for a blocked digestive system. How then are horses able to survive on a grassy diet? Ancient perissodactyls and other mammals had a unique pouch-like addendum to the stomach known as a cecum, which also adapted to serve new digestive functions but without developing the multi-chambered ruminant gut. In horses, the cecum evolved to house a specialized microbiome, capable of breaking down the tough bonds that make up cell walls in grasses and converting them into smaller, more easily usable compounds. In the horse's digestive system, dietary grass moves from the cecum into the colon, where after some last-minute resorption, it soon exits the body. The inefficiency of this system, relative to that of the ruminants, means that to meet their caloric needs, horses must graze continually, eating as much as 2.5% of their body weight in feed over the course of a day. Although teeth gave horses a powerful tool to deal with grassland environments, their need for continual grazing would influence their second major category of adaptations: speed and movement. Speed and movement. Even if grasses can be stomached, life in the prairie also requires water, and water sources are few and far between. Grazing enough territory to fulfill a horse's huge dietary volume quota thus requires endurance for long, regular movements. The exposed conditions of open grasslands also mean high risk of attack from predators, which can rarely be evaded through any other means besides speed. Early equids needed speed to outrun predators, and the endurance to cover large swaths of territory while grazing. Over the millennia, proto-horses responded to these challenges in myriad ways. Some were wildly successful, others resulted in extinction. Over time, Ancestral horses converged on a body plan with longer, more robust limbs, capable of immense strides, impressive musculature, and a specialized ligament structure that allowed them to stand continuously with little exertion, but also to spring quickly into action. In the genus Equus, the 3 and 4 toes of the ancestral equids, like Eohippus, were streamlined down to a single hoof capable of sustaining the large, swinging strides of increasingly large-bodied animals. This structure made them capable of fantastic stamina and velocity. Behavior and communication. While morphological and dietary adaptations were crucial to success in the grassland, behavioral adaptations were among the most important of all. Although speed is critical for evading predators, the protection offered by a social group can be even more impactful, especially for young animals trying to survive in an open prairie. The strength in numbers approach. Because of the advantages of group life in protecting the vulnerable, many medium-sized and large grassland herbivores evolved cohesive group structures and gregarious behavior analogous to the social systems evolving in parallel among early primates and other mammals. Present-day members of the genus Equus all display some form of group social structure, typically taking one of 2 forms. In the territorial system found in donkeys and zebras, and more common in resource-poor and desert environments, females and their young aggregate into small clusters, with males competing among themselves to monopolize the largest territory encompassing the range of as many females as possible. In the harem system, found in domestic horses and their wild sister species, the Przewalski's horse, all the females and young animals live together, and a lone lead stallion lives with them. Unaffiliated males aggregate into bachelor groups, ranging in size from a few to a dozen or more individuals. Strange as this system may seem to people today, this structure is quite common among mammals, including primates. Well-documented cases are found in langur monkey societies. Careful field studies show that living in these large social groups, wild horses form close relationships, and that they coordinate their grazing and sleeping patterns closely, making them a cohesive and coherent unit capable of protecting each other from predators and surviving in the challenging environments of the steppe. Horse social organization is also flexible, and some equids are even known to switch to a different social system when introduced to a new environment. The evolution of a dynamic herd life helped ancestral horses survive in the exposed environments of the prairie and steppe, especially throughout the many fluctuations in global climate that have occurred throughout evolution during the Cenozoic. Alongside these stable, long-term, and complex social relationships, horses also developed high intelligence and unique capabilities for communication. Perhaps because of their complicated social lives, modern horses have sophisticated social awareness, even eavesdropping on interactions between other horses within their group. Horses are also capable of complex learning, memorization, and concept formation. Although it is difficult to trace the antiquity of these social and behavioral systems in the fossil record, the key elements of horse society, including a hierarchy dominated by a lead stallion, sophisticated social relationships, excellent communication skills, and a tolerance for group life, likely helped the ancestors of horses navigate life in the grasslands of the ancient world. Horses, asses, and zebras. While many lines of proto-horses came and went over the last 50 million years, genomic research suggests that all modern equids descend from a single line belonging to the genus Equus that evolved in North America around 4 million years ago. Soon after, this lineage split into 2 deep divisions. These included the so-called caballine horses, that is, those that exhibit similarities to the modern domestic horse on the one hand, and the zebras, asses, and donkeys on the other. The genetic differences across these 2 lineages today are significant, eclipsing the degree of separation seen between humans and chimpanzees, perhaps reflecting a wide range of adaptations to diverse environments. Ancestral zebras and wild asses probably coexisted with early horses in North America exclusively until the Pleistocene, a mostly colder era, characterized by numerous quick and dramatic fluctuations between ice ages and warm interglacials that lasted from roughly 2.5 million years ago until about 15,000 years before present. During the first of these ice ages, both the caballine and zebra-ass donkey groups dispersed across the Bering Land Bridge into Asia, and by roughly 2 million years ago, into Africa. This Pleistocene era, with its sometimes severely cold, dry conditions, created difficulties for many animals and plants. Not so for equids, whose specialized adaptations to grassland life were perfectly positioned to benefit from these colder periods, when temperate rainforests dried up and gave way to grasslands. In North America, stout-legged horses, including the Yukon horse, lived alongside the slender-legged animals with ass-like traits that some researchers classify within equus, though others classify it in a separate genus, Harrington hippus. As animals spread out of North America, equus had a mini-radiation of its own. Recent genomic sequencing suggests that Eurasian caballine horses split from their North American ancestors perhaps around 1 million years ago, although several later dispersals across the land bridge brought more recent intermixing episodes. In Asia, warmer southerly latitudes became the favorable habitat of wild asses, which separated into a variety of subspecies, including the Tibetan Kiang, the Mongolian Hulan, and the Persian onager, while horses like equids, including the now extinct Siberian horse, Przewalski's horse, and the ancestor of the domestic horse, proliferated across the colder northern zones. In Europe, an as-yet unnamed lineage of wild horses inhabited Iberia and perhaps other areas. In Africa, asses and zebras adapted easily to the savanna. Africa developed 2 species of wild ass, the Nubian and the Somali, along with at least 3 species of zebra, and as an isthmus formed once again to connect the Americas across Panama, wild equids moved into South America as well, which boasted the small horse-like Equus neohius and species of Hippidian, ancient relatives of equus. There may well have been others, too, in all these places. Population estimates using genomic data suggest that wild horses reached their population peak roughly 40,000 years ago, when the ancestor of the domestic horse split from the Przewalski's horse into separate species. By the late Pleistocene, horses, asses, and zebras and their relatives lived on every continent except Australia and Antarctica. Summary. Over 50 million years, the descendants of the tiny dawn horse, a dog-sized creature browsing forest margins in the wake of the asteroid impact, had thus become consummate prairie animals, with specialized dietary adaptations for eating grass and elite anatomical and behavioral adaptations for speed and predator evasion in the open steppe. With the onset of the Pleistocene, the American equus radiated across most of the world's continents, diversifying into an impressive range of asses, zebras, and horses. Occupying areas that could sustain larger groups, horses developed harem societies with rich systems of communication and cooperation. In the colder conditions of the Ice Age, which kept the habitants of interior Eurasia cool and open, things were looking bright. As early members of equus spread across new continents, though, they would encounter another child of the extinction event, descended from the tiny proto-primates that paleontologists once confused with dawn horses. This primate had now become a deadly, opportunistic carnivore with a taste for horse meat. 2. Connection. As the world cooled, land bridges opened and early horses spread westward. As early as 2.6 million years ago, these hooved immigrants had reached Europe and the Indian subcontinent. Equus soon diversified and adapted to their new environments, with early zebra-like species excelling in the African savanna and asses flourishing in the mid-latitudes of Africa and Eurasia. With their higher tolerance for cold conditions, horses thrived in the grass and forests of high-latitude Asia and Europe. Unlike the Americas, however, these new continents were full of hominins, ancestral humans like Homo erectus and their close relative. These early humans had spread out of Africa for the first time and were experiencing their own adaptive radiation across the world, from Africa in the south and Europe in the west, all the way to the coasts of East Asia. By somewhere around 500,000 years ago, the early hominin Homo heidelbergensis inhabited all the regions surrounding the Mediterranean. Expert toolmakers and proficient hunters of large animals, they became the first human ancestor to succeed in colder climates. Across Eurasia, the destinies of these early hominins and horses would forever intertwine. It is difficult to say precisely when early humans first came into contact with early horses. Some evidence suggests that the very first humans to leave Africa might have interacted with relatives of the horse. In Georgia, the Eurasian Republic between Russia and Iran, a large assemblage of fossil bones at the site of Dmanisi, dating to around 1.7 million years ago, included both Homo and Equus within the same deposit. However, these Dominici equids were probably not true Caballine horses, and there is no direct evidence that early Homo found at the site was hunting or eating them. Whenever the first relationship between humans and
Sample complete. Ready to continue?